We've been treating Artemis 3 as the mission, the one that puts humans back on the moon for the first time since 1972. That's what everything has been building toward. The crew, the hardware, the countdown, the historic weight of it. But that plan is already starting to change. And the reason tells us something that the official statements haven't: how far away we actually are from a landing. Before we send anyone to the lunar surface, there's a chain of technical problems that have never been solved together in a single mission. Some of those problems don't yet have solutions, and that gap is driving everything we're watching unfold right now. What's being discussed inside NASA is moving Artemis 3 off a lunar landing entirely. The mission becomes a full system validation run in low Earth orbit, proving that all the pieces work together with real astronauts aboard before anyone commits to deep space. Under that scenario, Artemis 4 becomes the actual landing. That's a big shift, and it matters. Artemis 3 has been NASA's public face of the return to the moon. Sliding the landing to Artemis 4 is an acknowledgement that the system has gaps that need to be closed before a crew depends on it 250,000 miles from home. And if we step back, this follows the same logic every serious spaceflight program has used. We didn't go from zero to Apollo 11. We spent years in Mercury and Gemini, proving every piece before anyone left for the moon. That's the pattern. You don't lose a crew. So where does this actually break down? Here's what most coverage misses. A lunar landing isn't one thing. It's a chain, and every link has to hold. If one fails, the mission stops. Full stop. Walk through it with us. SLS launches Orion into orbit. Orion rendezvouses with the lander in cislunar space. The crew transfers between two completely different vehicles. The lander descends to the surface. Astronauts work the South Pole. The ascent stage brings them back to orbit. They redock with Orion, and Orion brings everyone home. 8 steps. Each one depends on the last. Each one involves hardware and procedures that have never been tested together in a real mission. Each one involves hardware, software, and crew procedures that have never been tested together in an operational mission. Near the moon, if something breaks in that chain, the options are gone fast. No abort window, no one nearby, and a crew that is days from Earth with finite consumables and no rescue timeline. That's the gap, and that's why proving this in LEO first isn't overcaution. It's the only rational path. Of all the unsolved problems in that chain, this is the one that keeps engineers up at night. Starship HLS cannot leave Earth fully fueled. The vehicle is simply too large and too heavy for a full propellant load at launch, so the plan is to fuel it in orbit. Multiple dedicated tanker launches, rendezvous with a propellant depot, transfer fuel, repeat until the lander has enough propellant to reach the surface and come back. Here's the problem. The fuel doesn't behave nicely in space. The propellants are cryogenic, liquid oxygen and liquid methane, and they boil off. Managing that boil-off across the window of multiple tanker launches without losing enough fuel to compromise the mission requires thermal management systems and transfer hardware that are still under development. The timing across those launches has to be exact. One slipped launch, one failed rendezvous, one transfer anomaly, and when the crew arrives, the fuel isn't there. This has never been done at this scale, not even close. We're not talking about a gap at the edges of the program. We're talking about a gap at the center of it. And the refueling problem isn't the only one. Orion has to dock with the Human Landing System, 2 vehicles built by completely different teams, under different programs, with different design assumptions. Starship HLS from SpaceX, Blue Origin, and Orion from Lockheed Martin. None of them were designed together. Before we ask a crew to execute that transfer near the moon, where a failure means being stranded in lunar orbit, we need to prove it works in LEO first, where an abortion takes hours, where engineers can see what broke, fix it, and try again. Near the moon, that margin disappears entirely. If docking fails out there, there is no second attempt. The crew doesn't have the time, the consumables, or the proximity to Earth to wait it out. That's the gap LEO validation closes, and it's a gap worth closing before we need it. And then there's the suit. The AXIM-U, Axiom Space's extravehicular mobility unit, keeps astronauts alive once they step onto the surface. If it fails on the lunar South Pole, there is no recovery option. No workaround, no way to call for help, and no second crew coming. The Apollo suits were built for short stays near the equator, where conditions were relatively well understood. We're going somewhere completely different. The lunar South Pole has permanent shadow zones. temperatures that drop to minus 170 degrees Celsius, and dust that is sharper and more abrasive than anything Apollo ever encountered. The XMU is designed for that environment. Greater mobility, improved dust mitigation, and a different life support architecture built for repeated South Pole operations. Right now, it's still in neutral buoyancy testing and simulated environments. Whether it gets validated in actual space conditions before anyone wears it on the surface is an open question, and it matters because a suit tested only on Earth carries a residual risk that no pool, no lab, and no simulation can fully eliminate. The South Pole doesn't offer a trial run. That's the reality. So here's the next question. Who's actually building the lander? Two companies hold contracts for the human landing system with NASA. SpaceX won the first in 2021. Blue Origin protested, lost, then received its own separate HLS contract in 2023. These are genuinely different bets on how we get to the surface. Starship is the biggest, most ambitious vehicle ever contracted for a crewed NASA mission, built for scale, full reusability, and eventual operations far past the moon. Blue Moon is a purpose-built lander, designed specifically around what Artemis needs at the South Pole, with a more traditional modular approach. NASA running both programs is a deliberate risk hedge. The technical uncertainty in each architecture is real. If one falls behind, the other holds the timeline. Which one is ready first, and which one performs when it counts, will shape how we operate on the moon for the next decade. That matters more than the brand competition. There's one more layer that's shifting the dynamic around all of this. Jared Isaacman is now the NASA administrator, and his background is unlike anyone who has held that role before. He's the first to come from the commercial operator world, having personally flown on commercial spacecraft and built a business inside the commercial space ecosystem. That changes the lens through which Artemis sees every decision. In Senate testimony, he framed Artemis in explicitly strategic terms, a race with a real competitor on a real timeline, where falling behind carries consequences. Less tolerance for schedule drift, more pressure on execution and commercial leverage. Whether that posture accelerates the shift of the Artemis 4 landing or pushes to compress the validation timeline and get there faster is the tension we're all watching build right now. Here's what's easy to lose in all of this. A mission that doesn't land might be the most important mission in the entire Artemis program. If Artemis 3 becomes a validation run, it's the gatekeeper, the mission that docks Orion with the lander for the first time with a real crew aboard, the mission that proves the propellant transfer produced a fueled vehicle actually ready for operations, the mission that puts astronauts in the XMU in actual space where no simulation can substitute. It produces the data that either clears Artemis 4 for a landing attempt or identifies exactly what still needs fixing before we try. Artemis 3 decides whether Artemis 4 lands. The mission that doesn't touch the surface may be the one that makes the surface possible. And none of this is happening in a vacuum. China's crewed lunar program is targeting 2030, and that timeline hasn't slipped publicly. They've put robotic landers on the surface, returned samples, and built a growing network of international partners around their own lunar architecture. The clock is running, and it's running whether Artemis is ready or not. Every month Artemis spends validating systems is another month that the perception gap grows, and it compounds. Inside NASA, a delay is a technical event. Outside NASA, in the partner agencies, the policymaker offices, the budget committees, it's a signal about the trajectory and about whether this program is actually executing. In a race where perception shapes political will, which shapes funding, which shapes capability, testing timelines are never just technical. That's the pressure sitting atop every decision we're watching NASA make right now. So here's where we actually are. The mission that was supposed to put us back on the moon may now be the mission that proves we're ready to try. The refueling problem, the docking problem, the suit problem, and the validation problem. That's the honest story of Artemis right now. And the gap is real, but it's closable. The first crew to stand on the lunar South Pole will get there because every link in that chain was tested, proven, and cleared before anyone depended on it. Artemis 3 might be the mission that builds that chain. It may not be the mission history celebrates, but it might be the one that makes the mission history celebration possible.